Let's talk about Earth's shape. I have a secret to tell you, one that shouldn't come as a surprise. The Earth is round. Yep, you heard it here first. Actually, that was known in ancient Greek times by Pythagoras, Aristotle, Eratosthenes. These were ancient Greek mathematicians who used math to kind of prove that the Earth was round. They did basic observations, but then backed it up with mathematical concepts. So this was well known for a while. It was Christopher Columbus that I think most people gave the credit to, that he discovered that the Earth was round. And that's actually not true. It's a myth, because most people at that time knew that the Earth was round. It was just that Columbus set out to prove it, to kind of make sure that everybody knew that that was true. See, the sailors had this fear that if you continued to sail past the horizon, you would fall off the Earth. I mean, that sounds crazy and ridiculous to us now, but this was a time when people believed that. So what we're going to talk about is how we can prove that the Earth is round and what our evidence is. There are four, so let's start. Our first piece of evidence comes from the moon. Okay, it's not so much that the moon shows that the Earth is round, it's what happens to the moon. These are the phases of the moon, and these phases could only take place if the moon was round, right? Different portions, different sizes lit every month, or every day of a month, has to do with the moon being round. But Aristotle was watching a lunar eclipse, and during that lunar eclipse he saw that the moon had a shadow cast on it. And that shadow, when you look at it carefully, was curved. Now we know that during a lunar eclipse, the Earth moves into a position that covers the moon. So the shadow that's being cast is from the Earth. And since it was a curved shadow, that has to mean that the Earth is round as well. So our first piece of evidence is that if the Earth casts a rounded shadow on the moon, then the only shape that the Earth can have is a sphere. Let's look at our next piece of evidence. So this is the ocean and the horizon in the background. The horizon is that black line that kind of marks the distinction between the edge of the top of the ocean and the atmosphere. If we were to watch a boat sail across the ocean over time, it would suddenly hit a point where it would start to disappear and fall out of view. And why that happens is because the Earth itself is curved. And if the Earth is curved, as we're looking at that ship sail away from us, it's following the curve of the Earth as it sails away. So that's why it falls out of our horizontal sight, because we're only able to see in that flat plane and not see the curvature that continues. To give you an example, this is the city of Toronto. You can see the Space Needle all the way on the left. That's one of its famous monuments. And it looks like this city is rising out of the ocean, which it's not an ocean actually, it's a lake. But the point is that it sits at a point from this photographer, where the photographer took the picture. It sits at a place where the curve of the Earth is showing the city lower. So the city actually looks to be somewhat below the waterline, which is not true. The city is actually above the waterline. It's built that way. It's because of the curve of the Earth that it appears to the viewer like that. So as objects appear to sink over the horizon, they are really passing on the curved surface of the Earth. Let's talk about our third piece of evidence. So here's our Earth, and if we were to strip away the outer layers, this is what we would see. Our Earth's interior. And standing on the Earth, we feel a pull towards the center of the Earth. That pull we call gravity. We actually measure our gravity in a quantity called weight. Our mass times our gravity. And it turns out that our gravity is pretty much the same on Earth no matter where you are. so our weight doesn't change. Now, if Earth had a different shape, let's say Earth was a football shape, well, if we were standing at this point on our Earth, we would feel a pull towards the center, right? Our weight. But if we were standing here on our Earth and felt a pull towards our center, we would have a very different weight. Why? Because we're technically in this situation closer to the center of the Earth. See, gravity is a force between two objects, and the closer they are to each other, the stronger the weight, or the gravity. The further they are, the weaker the gravity. And in this situation, if the Earth was shaped this way, we would have a much stronger pull standing at this position. So on our present-day Earth, no matter where we are, our weight is exactly the same. Therefore, our gravity is exactly the same. So if that's true, then Earth must be a sphere. If the pull of gravity is just about equal from all points on Earth, Earth has to be round, or at least spherical. Our fourth piece of evidence is probably the best: photographs. So something happened in 1972 that hadn't happened before. We sent our Apollo 17 spacecraft to the moon. It was a manned spacecraft, so astronauts were involved. And as they left Earth's orbit, they turned their spacecraft and snapped this picture. So what you're seeing is the picture from that spacecraft from 1972, clearly showing a round Earth. Here's another picture taken by the Galileo spacecraft in 1990. It's actually a series of pictures put together in a time-lapse video, demonstrating that the Earth is rotating, but also spherical. So our fourth and best piece of evidence comes from photographs. Today we have satellites, we have an International Space Station, and countless manned missions and unmanned spacecraft that have snapped pictures of other planets, and all of those planets also being round. So in our next video, we'll see how planets did get their shape and discover the forces that designed our solar system. Thanks for watching.